Okay, so the first the place I want to start is something that came up in András's talk, but let me highlight it. We're going to say that a knot K in S3 is slice in some 4-manifold X, which is closed and oriented, if K is the boundary of a disk embedded smoothly in X. Everything in this talk is going to be smooth. So what's the picture you should have in mind? You have your 4-manifold X. And right now, there's not really anywhere to put a knot. So you remove a ball, which gets you an S3 boundary. We'll call that X circ. And what you should be imagining is that whatever knot you're interested in lives here. And you're asking that it bounds a D2 like this. Okay, so that's a definition a lot of us are familiar with because one of the questions that motivates quite a lot of people in the collaboration is this question of whether there exists a knot K. Well, let me say instead, whether there exist 4 manifolds, X and X prime, which are homeomorphic, and which come with a knot K, which is slice in one, but not the other. And maybe some notes about this question, fairly obviously, but if yes, then that's going to distinguish the 4 manifolds smoothly. And if yes, and X prime is S3, 4, then you disprove the Poincare conjecture. And sort of this question, in particular here, and in particular possibly approached with a variance from Kovanov homology is something a lot of us think about. So this is the question that the talk will kind of be based around. But this question is too hard. We don't have any answers to this. That's surprising because, as you just saw, we know a lot about exotica, but we don't know how to distinguish manifolds by distinguishing the set of knots that are slice in one and not the other. So what I want to talk about today is an easier version of this question, where instead of asking that the manifolds be homeomorphic, I'm just going to ask that they have the same cohomology ring. Not visible. Great, thank you. Okay, yellow. Oh, if there is, I'm not going to figure it out. Somebody else is welcome to. Okay, so I'm asking, the modified question is instead of asking that they be homeomorphic, just ask that they have the same cohomology ring. And maybe the kind of hardest version of this question, kind of in analogy here, would be to, again, demand that one of them be S4. So what are you asking? You're asking for a integer homology 4-sphere and a knot K, which is slice in that thing, but not in S4. And that doesn't imply anything, except we'd really like to know that. It's kind of become a bit of a touchstone, at least to me, question. So I'm not going to answer this question in the S4 setting today, but the theorem I want to tell you about, which is joint with Ty-Lidman, is an answer to this question in maybe the next simplest setting. So there exist 4 manifolds, Q and W, with the following properties. That doesn't go up anymore. OK. What do we have? The homology of Q matches the homology of W and is Z mod 2 for all of the things where it could possibly be interesting. One of them, Q, in fact, has very simple fundamental group. And the figure 8 knot is slice in Q, but not in W. Maybe a sort of final comment about the statement. Here, this question in the S4 setting is you're kind of asking, can you answer this where one of the 4 manifolds is like this very standard thing? And well, you might not have like a standard closed 4 manifold with this homology in your pocket, but there kind of is one. So I'll define it in a minute, but let me say that Q is in fact, well, Andras defined it quickly last time as well. Q is this standard 4 manifold, which maybe I'll call the Kawauchi manifold. So this is indeed some standard thing. Questions about the statement? On the record, no. Other questions? On the record, no. More questions? Cool. OK. So the plan for the talk is, of course, to sketch a proof of the theorem. But along the way, I want to give some other constructions as well. This theorem is, in fact, not what we were trying to prove. It kind of fell out of a larger project, which involves kind of studying the constructions of exotic 4 manifolds that people were using in like the aughts and combining it with some stuff that Ty and I like to think about. And in that process, I learned how people built exotic manifolds in the aughts, which I always thought was like gnarly and impossible, but is actually pretty nice. So I want to, and the tools here are inspired by a lot of that. So along the way, we'll kind of see some of those constructions. So first off, we'll build a 4 manifold Z with the cohomology of S2 cross S2, and but which is not S2 cross S2. So this is not a new result. This is originally something that was built by Fintischel, Park, and Stern. Then we'll build these guys. So W, rational homology ball, sphere, which is not this standard one. Going to need that to prove the theorem. And finally, and I'll mention this a little more briefly, I'll build X, which is in fact exotic, so homeomorphic and not diffeomorphic, to CP2 blown up 5 times. That's also not a new result, originally due to Park's Sabo, not the same Park. And there's a lot of proofs of this in the literature nowadays, but I want to give one that kind of combines classical techniques with some stuff Ty and I like to think about. Questions here about the plan? I like to get a lot of questions, so I'm not. Do I know it's not the same? I guess not. I guess not, yeah. How does the figure 8 enter here? Great question. First off, kind of on the nose, it actually doesn't. I want a strongly negatively amphichiral knot with ARF invariant 1. I just think sometimes abstraction is hard. It makes things worse. It'll show up in the construction, though. You'll see it. Because when I say cohomology, I'm kind of just insisting that the intersection forms also match. But here, all the H2 is torsion, so more questions. No, it's not going to be H slice in Q. More questions. OK, cool. Please feel free to stop me. Oh, interesting. Oh, I need that board back. OK, so before I can kind of build these interesting examples, I want to start by setting up the standard objects, right? All of these statements, I'm kind of building something and then comparing it to something standard. And I think most people in this room don't need me to tell you how to build S2 cross S2, but I'm going to do it anyway. I'm going to construct all three standard objects in a slightly non-standard way that will then parallel for the non-standard construction. So we'll start with that. I'm going to build these three four manifolds for you. OK, so there's three of them, but they're all going to come from this kind of essential piece. So we'll call that manifold 0. And the essential piece is going to be the 0 trace on the figure 8 knot. So what's that? It's the manifold you get by taking a 4-ball, boundaries S3. Think about, wow, carpet didn't break. Think about the figure 8 knot in that boundary. And now basically you just want to glue a disk onto the 4-ball where the boundary of the disk is getting identified to this knot. So you kind of have this D2 here. Of course, that's not currently a 4 manifold, so we're going to thicken it up. And this is the trace. OK, so that's like this nice, simple 4 manifold with boundary. Let me point out some properties it has. First off, it's got the same cohomology ring as S2 cross D2. So I'm going to think kind of, as far as homology is concerned, we could pretend it's that. It's also simply connected. It's a ball and then add a relator. And maybe the one thing that's slightly less obvious about it is that the boundary admits an orientation reversing free involution. And maybe let's call that G. And this is coming from the fact that the figure 8 knot is amphichiral. Questions here? Yeah? Oh, thanks. Is trivial. It has pi1. That's the statement. The pi1 group is defined. Other questions? OK, great. So we're going to use this piece to build all of those manifolds that you already know about. Here's the first one. We're going to take the 0 trace and another copy of it. And we're going to glue them together using this involution. Because this is orientation reversing, this is an oriented 4 manifold. Kind of because of the homology here, it's not hard to check that it's got the homology type of S2 cross S2. Also because this is simply connected, it's simply connected. So this is a candidate for exotic S2 cross S2s. But of course, like that would be way too easy. It's not exotic. It's actually S2 cross S2. OK, good. Second object. There's actually a free symmetry G on this entire thing, which comes from exchanging the components. So I can take the quotient, and I get a 4-manifold Q. So that's the definition of this standard 4-manifold. Pi1 of Q is Z mod 2 because it has a simply connected twofold cover, and it's not hard to check that. In fact, all the interesting homology groups are Z mod 2. And maybe a final remark about it is that it's also spin. Okay. And the third standard object, and this is going to look a little contrived here, but you'll see the parallel once we build the non-standard one. You could also take the 0 trace on the figure 8 knot, and then glue to it the 0 trace on the figure 8 knot connected some with 4 CP2 bars. OK, of course, actually, it doesn't matter where you put these CP2 bars. So this is CP2 blown up 5 times. But this setup kind of parallels what we'll do later. So questions here about the standard objects or anything else? I'm exchanging them. If you doubled it, you would usually want to use the identity as your gluing, which is orientation preserving. So you'd want to flip the orientation on this manifold. Here? In 3, thanks. Yep. Yeah, it is, if you factor through that. Yeah. But I kind of want to say it like this. More questions? OK, great. So those are our standard objects. So we can start building our non-standard objects. Start with step 0. We need this essential piece. We'll call it V. And before I kind of just jump into building it, let's ask what do we want it to have. So here's like the wish list for V. So the properties that were important about the 0 trace on the figure 8 knot to make all of these constructions were that it was a homology S2 cross D2, that the boundary had an orientation reversing free involution. We liked that the fundamental group was trivial. Gave me trivial fundamental group up here. And this can be weakened, and this is something we didn't have before, but I'm going to ask for V to be symplectic. That's going to make my life really easy when I try to distinguish whatever I'm building from the standard object. OK, so I want to try to build something like this. And knot traces maybe look like a good source of examples. Maybe I could just take the trace on some more complicated knot. But in fact, these are mutually exclusive for knot traces. So we're not going to be able to just use a not trace for this. We're going to have to do something a little worse. And it's going to be actually kind of a lot worse. We're going to give up on this. This is too hard. So we'll try to build something like that. Questions here? I'm teaching a class right now where like I can't get a word in. It's just like question time all the time. So apologize if I ask like too often. OK, so how are we going to build V? Well, let's start off by taking a bundle, a surface bundle over surfaces. Those are nice examples of four manifolds. And let's take one where you're going to have genus 2 fibers. And the base is a punctured torus. So you should be picturing, maybe here's your base. Here are your fibers. Something like this. And OK, this is going to have some monodromy. Let's just give it a name. Maybe if you have curves like C and D in the base, then your monodromy, maybe you want to call it like MC and MD. So this has a couple of nice properties. One is it's just like a four manifold that you can write down. That's good. Another nice property is that it's going to be symplectic. So we kind of hit this, at least as long as we kind of don't lose symplecticness. But what's not good is that you have a whole lot of H1. In particular, like H1 of E is going to surject H1 of T circ. That's a problem if you want this. So we want to take this bundle and we want to modify it to get rid of this H1. By the way, you might have more homology too, depending on what your monodromy is, but that could be killed by a good choice. So Andras mentioned last time very quickly that there's a kind of standard technique for getting this homology out of here. So let's assume, for example, that there's some curve alpha on the fiber. Maybe, I don't know, something like this, which is fixed by the monodromy, I don't know, over C. That means that if I kind of transport alpha around C in some section, it's going to come back to itself. So we get a torus embedded in our manifold. Let's call this T alpha C. And now I want to make some observations about it. Turns out it's zero framed, so its neighborhood is just going to be T2 cross D2. And in particular, the boundary of that neighborhood is going to be T2 cross S1, which there's a reason I'm writing this. I'm not just being pedantic. Of course, that's just S1 cross S1 cross S1, T3. And we kind of know where each of these factors came from. They came from maybe like alpha C and the boundary of D2. So what have we done so far? We've observed that there's this torus in our manifold, and one of the curves in homology of the torus is one of these curves in homology of the base that we'd like to get rid of. And so the fix is to remove the neighborhood of the torus. and then re-glue it so that the boundary of the disk in the neighborhood of the torus gets mapped to C, this curve I want to kill. You can do that sort of because T3 has a whole lot of homeomorphisms. So good, that looks good as a strategy for killing H1. It's like a mild lie. I don't quite want to go to C. I want to go to C plus boundary of D, but don't worry about that. And this operation in general has a name. This is what's called a Lettinger surgery. And a nice fact about it is that if you do it well, then you can get a symplectic manifold at the end as well. So the plan then to build a piece V satisfying the wish list is to do something like this. So the lemma, there are choices of monodromy such that after 2 Lettinger surgeries, 2 because I need to kill both C and D, you get a manifold V which satisfies the wish list. Questions? You don't, and in general, probably doesn't. Your monodromy has no reason to be reducible. You do have to be careful here to make sure that there are going to be tori. More questions? OK, so then we can now build manifolds exactly in analogy with these ones here. So 1, Z will be defined to be V union V, where the gluing is along this orientation reversing free involution that we made sure V had on the boundary. The homology of Z, cohomology, is going to be the cohomology of S2 cross S2. And in fact, Z is, this sort of cover is still going to be symplectic. And you can invoke a really nice result of Stipchus and Szabo. Which says that in manifolds that have some properties that Z has, any smoothly embedded surface, which is in a non-trivial homology class and has self-intersection 0, has to have large genus, or sort of large genus. One way to see it, so first answer is like, you need me to tell you what F is. But then maybe let me tell you something about F. I could have actually built Z as just working over a genus 2 base the whole time, and then doing 4 Lettinger surgeries, so that's going to be symplectic. No, I'm not. Actually, I would like to talk about that. Yeah, thanks. More questions? OK, great. And sorry, so why did I state this theorem? Well, because this is going to show us that this thing is definitely not S2 cross S2, which definitely does have low genus surfaces in non-trivial homology classes, square 0. So there's no claim about the fundamental group of this, but still, this is a homology S2 cross S2. I didn't know how to build those for a long time. And I want to comment here that this construction is following pretty closely the construction of Finchishall, Park, Stern. OK, great. So 2, we're going to get the manifold W from the theorem. Exactly as before, we have this free involution F on Z. Maybe I should write it over here. And orientation preserving. So again, we're getting W by taking the quotient of Z by the involution. And so what are our observations about W? Well, as before, W is going to be a rational homology S4. It's going to be spin, has the same homology groups as Q. You can already see that W is not the same thing as Q because, as Andras said, they don't have the same twofold cyclic cover. We'll prove that again by showing that there's a knot that's not slice in here, or that 4-1's not slice in here. And 3, and this is what I'll say maybe the least about, but here, for this piece that was kind of contrived in this setup, we're going to use something more interesting. So with Ty and Adam a few years ago, we built a 4-manifold M that has some nice properties. So the boundary of M is the same thing as the boundary of V. The homology type of M is the same thing as the homology type of V connected some 4 CP2 bars. And this is what you really wouldn't get if you just took V and summed it with a bunch of CP2 bars. Pi1 of M is trivial. So now you can take V, we'll define this final manifold X to be V glued to this M. And so V is, well, I made no claims about what its fundamental group is, but because M is simply connected, and with a little more work, you can show that X is going to be simply connected. And X is a homology, CP2 blown up 5 times. And what I won't argue today, but isn't too hard following some other properties we established about M, is that X can't be CP2 blown up 5 times. Questions here? The basic, so this has basic classes, okay, but so does this. But you can show that there are basic classes here that have a large evaluation on a square 0 surface. Large, kind of large. Larger than what it would be for the other one. More questions? If you stabilize with With what? Yeah, it falls apart. More questions? Yes, I do. Sorry. Let's say again, kind of because it's coming from this cover that has exactly the same homology as when we built Q. So the plan for the rest of the time is to outline a proof that the figure 8 knot is slice in Q and not in W. And to do that, I need a lemma, which is a lemma I always think I will never have to state in a talk again, but here we are. So the lemma says that a knot K, actually let's just apply it to our very specific case. The figure 8 knot is slice in either Q or W. Just pick one for the statement, both are true, if and only if the zero trace on 4,1 embeds smoothly in Q or W, respectively. Okay, so I'll sketch one direction of this. I think there's lots of people here who haven't seen this. Anybody have a preferred direction you want to see? You want that way, okay? All right, so we're assuming that 4,1 is slice in one of our manifolds, let's say Q. So let's get a picture of that going. Here's Q. What does it mean for the 4,1 to be slice in here? Well, we have to actually punch out a ball. So there's our punched out ball. And we're looking at 4,1. And the hypothesis is now that we have this nice smooth disk here that 4,1 bounds. Disk is smooth, so it's got a tubular neighborhood, which is a D2 cross D2. And now we are in pretty good shape because this is a 4-ball with a D2 cross D2 stuck to it along 4,1. So that's the trace. Sitting now inside Q, because maybe I'll put that ball back.
Blue is still invisible.
Oh no, blue is invisible and green is not? Maybe you can't tell. They're both, oh boy.
Was that green?
I don't, let's, okay. Yeah, so what happened, we had a disk that 4,1 bounded. Disk had tubular neighborhood. And now if I look at the ball that I removed and the neighborhood of that disk, what is that? That's a B4 with a thickened up disk stuck to it along 4,1. So that's the zero trace on 4,1 sitting in Q. Questions? Because the H2 is Z mod 2, so whatever framing it is had better square to 0, since it has to go to the 0, the trivial homology class. More questions? Okay, great. So to prove this, we have to prove two things, sliceness in Q and non-sliceness in W. For A, we're actually in super good shape. We're just going to notice that the zero trace on 4,1 embeds smoothly in Q by construction. So where's Q? Here it is. So how did we get Q? Well, we started with this S2 cross S2 built out of two of these zero traces glued together, and then we took the quotient. So if you just look at this one and maybe like lose a color near the boundary, that's still one of these, and it's embedded in Q. Okay, why not in W? Well, first, let me get kind of, so if for one we're going to be sliced in W, then that's the same thing as the zero trace embedding in W. And, well, then there's kind of two things that could happen to that map on H2. It could either, like, this has one generated of H2, so it could either go to the 0 or to the non-trivial class in H2 of W. So let me first rule out it being trivial. So it's a kind of classical theorem in, I don't know, knot theory that I could not find a citation for. And then I asked a lot of people, and it's not in the old literature, so maybe C. Klug. But that's not really the timeline for this. So what does it say? It says if the RF invariant of a knot is 1, and the zero trace on K embeds in any spin rational homology S4, then the induced map on H2 has to be non-trivial. So now if I want to show that the zero trace on 4.1 doesn't embed in W, it suffices to show that there does not exist such an embedding. Suppose for a contradiction that there was such an embedding. And notice that there's a T2 embedded in the zero trace on 4.1 generating H2. That's because it's a genus 1 knot. So you can take the Seifert surface, cap it off with that disk we stuck to it. That's a nice torus sitting in here. And this is sitting in here. So in fact, we're going to get a T2 in W. It has to generate. Okay. And now we can look at this twofold cover of W, lift this T2 up to Z, and we're going to get an embedding of T2 in Z, where at least we know that the class, it lives in some non-trivial class. And you can also check it still has to be square 0. But that's a contradiction, because Stipshitz and Szabo told us that there can't be low genus surfaces in Z with square 0 and in the non-trivial class. Questions here? Yeah. Because H2 of W is just Z mod 2, and I'm assuming that this map is not the 0 map. So yeah, not many options. Cool. So I think this is like the first time in my life that I ever went under on a talk. But that's what I had to say. Thanks.